The 3SLS model is an extension of the 2SLS approach. Both 2SLS and 3SLS take a similar approach to solving the problem of endogeneity and simultaneous equation bias. In fact, the first two stages of 3SLS model are the same as that of 2SLS. To understand how 2SLS and 3SLS solve the problem of endogeneity or simultaneous equation bias, let us go back to Tutorial 1. In Tutorial 1, we defined the simultaneous equation bias and the source of that bias. In the simple model shown here, we were able to show the source of the bias by substituting the first equation of y into the second equation. When we bring x to the left-hand side and rearrange, we are left with the equation shown here. Here, we can see that x is a function of exogenous variable q. But x is also a function of the error term mu. This error term mu appears in the first equation of y, which means that the independent variable x and the error term are related in the first equation. This causes the bias in the estimates. The 2SLS and 3SLS models give us a solution to this problem of endogeneity. If we look at the equation here, we can clearly see that the bias arises from the last component of the equation because it contains the error term mu from the first equation. If we can somehow remove this component and keep only the first part of the equation, then x and mu will no longer be related. The issue is that this component contains the error terms mu and upsilon, which are not observable directly. But, if we look at the equation carefully, it simply expresses the variable x as a function of exogenous variable q. That is, the endogenous variable x is a function of exogenous variable q. This is called a reduced form equation, which represents the endogenous variables in terms of all the exogenous variables in the model. If we estimate this equation, we can obtain all the components that we need. The error term epsilon shown here contains the component that causes endogeneity and bias. By removing this error term epsilon and keeping only the reduced form coefficients and exogenous variables, we can get rid of the bias problem. This is exactly what 2SLS and 3SLS models do in the first stage. The estimates or coefficients obtained from 3SLS will be more efficient than 2SLS estimates. This is because the 3SLS is a systems method, that is, it estimates all the equations of the model together. This is different from 2SLS, which is a single equation approach and estimates the equations one by one. This means that 2SLS uses only the variables that appear in the model but does not consider the structure of other equations in the model. Moreover, it does not consider the interdependence of error terms of different equations. Given the complexity of economic relationships or economic variables and the fact that some endogenous variables appear on the right-hand side of the equations, it is generally expected that the error terms of different equations will be related. 2SLS ignores this aspect entirely. On the other hand, 3SLS includes an extra third stage which deals with this issue. Therefore, the 3SLS model accounts for the dependence of error terms of different equations and considers the entire structure of the simultaneous equation model. Since it uses more information than 2SLS, the coefficients are more efficient as well. Now, let us illustrate all the three stages of the 3SLS model using an example. Let us consider a simple model of income determination to show how 3SLS is estimated stage by stage. The model shown here consists of 3 equations and 3 endogenous variables. The third equation is the identity equation and does not need to be estimated. So, we have to estimate the consumption and investment equations using 3SLS. Here, consumption, investment and income are endogenous variables and lag of income, lag of consumption and government expenditure are exogenous and predetermined variables. The endogenous variable of income appears on the right-hand side of the equations and is related to the error terms mu1 and mu2. This will cause the problem of endogeneity and bias, and we will use the first stage of 3SLS to get rid of this bias and endogeneity. Moreover, 3SLS will account for any dependence between the error terms of consumption and investment equations. That is, the 3SLS model will consider and incorporate the correlation between mu1 and mu2 in the third stage to estimate the coefficients. The first stage of 3SLS is the same as that of the 2SLS model. Both 3SLS and 2SLS use the first stage to get rid of the bias and endogeneity problem. In this first stage, we have to estimate the reduced form equations of endogenous variables. As discussed earlier, reduced form equations express the endogenous variables as function of all the exogenous variables. In our example, YT or income is the endogenous variable which appears on the right-hand side and causes endogeneity and bias. Therefore, its reduced form equation will express YT as a function of all the exogenous variables in the model. Our model has three exogenous and predetermined variables: lag of income, lag of consumption, and government expenditure. Therefore, we have to estimate the reduced form equation shown here. As discussed at the beginning of this tutorial, the error term epsilon is the component that is causing the problem of endogeneity and bias. The remaining component, including the exogenous variables and reduced form coefficients, will not lead to endogeneity because this part will not be related to the error terms mu1 and mu2. Now, we can obtain the predicted value of income or YT cap. The error term or epsilon has been removed from this YT cap component. Hence, we have managed to separate the component causing endogeneity using OLS in this first stage. The predicted income or YT cap is separated from the epsilon component that caused endogeneity and can be used in the second stage of 3SLS. In stage 2 of 3SLS, we use the results from the first stage to estimate the equations of the model. In stage 1, we obtained the predicted values of income or YT cap from the reduced form equation. Here, we use those predicted values or YT cap as an instrumental variable for YT or income. As a result, our equations will look something like the ones shown here. All the other variables stay the same, but the endogenous variable income is replaced by an instrumental variable YT cap. This works because the YT cap will not be related to the error terms. The component causing endogeneity and bias was removed in the first stage of 3SLS. The estimates or coefficients of these equations will give us the 2SLS estimates. However, this is where the similarities between the 2SLS and 3SLS model end. We are not interested in 2SLS coefficients here, but we will use these results to obtain the estimated residuals mu1 cap and mu2 cap. These estimated residuals mu1 cap and mu2 cap will help us account for the correlations between the error terms across equations. Using the estimated residuals mu1 cap and mu2 cap from the equations, we construct a variance-covariance matrix of estimated residuals. In general, the variance-covariance matrix of residuals will look something like the one shown here. The first element is the variance of the error term of equation 1, that is, the variance of mu1 cap. The second element here is the covariance of error terms of the first and second equation, that is, the covariance of mu1 cap and mu2 cap. This way, we estimate the variance and covariance between all the estimated residuals of all the equations in the model. This variance-covariance matrix will end up being an E by E matrix, where E is the number of equations in the model. In our example, we have two equations, therefore, this will end up being a 2 by 2 matrix. The first element is the variance of mu1 cap. We estimated this residual mu1 cap for equation 1 earlier. The second element is the covariance of mu1 cap and mu2 cap. The third element will be the same as the second element, which shows the covariance of mu2 cap and mu1 cap. The last element is the variance of mu2 cap. This estimated variance-covariance matrix will be used in the third stage of 3SLS. Using this matrix, we will be able to incorporate the relationship between error terms of different equations into the model. Now, we move on to the third and final stage of the 3SLS model. In this stage, we will use the information from the first two stages to estimate the structural coefficients of the simultaneous equation model. From stage 1, we will use the predicted values of the right-hand endogenous variable income. These predicted values will be the instrumental variable and replace the original income variable. This will ensure that we can eliminate the bias and endogeneity problem from the model. From stage 2, we will incorporate the estimated variance-covariance matrix of residuals into the third stage. Using this matrix, we will be able to account for the correlation between the error terms of different equations in the model. The formula shown here is used to estimate the three SLS coefficients. This formula represents the generalized least squares or GLS type of transformation of the variables. In this GLS transformation, the components shown here contain the variance-covariance matrix estimated in the second stage. This component is the weight matrix, which is used to transform the variables of the simultaneous equation model. Hence, the variables have been assigned weights based on the variance-covariance of residuals from the different equations. Let us take a closer look and show what each element in this 3SLS formula represents. First, the matrix Z cap shown here contains the independent variables of all the equations in the model. Remember that 3SLS is a systems method that estimates all equations simultaneously. Within this Z cap matrix, ZC is the independent variables in the first equation of consumption. These variables are stacked in such a way that each column contains all the observations of the variable. For instance, the second column of ZC contains all the observations of YT cap. This YT cap is the predicted values of income that we obtained in the first stage. It acts as the instrumental variable for income. The first column of ones is needed to estimate the constant beta 1 of the consumption equation. The third column contains all the observations of lag of consumption. Similarly, Zi contains all the independent variables of our second equation of investment. The columns are again stacked in a similar way where the first column of ones is for estimating the constant alpha 1. The second column contains all observations of YT cap from the first stage and third column has all the observations of lag of income. The ZC and Zi are further stacked within the Z cap matrix in the following manner. This means that Z cap will end up being a matrix with n by 2 rows and 6 columns. The n here stands for the number of observations we have for the data. We will have n by 2 rows in Z cap because we have 2 equations. Further, Z cap will have 6 columns because we have a total of 6 coefficients to be estimated in the consumption and investment equations. The Z-cap transpose matrix shown here is obtained simply by taking the transpose of the Z-cap matrix. Hence, it will have 6 rows and n by 2 columns in our example. If we take a look at the weight matrix shown here, it contains 2 elements. The first element of sigma cap is our estimated variance-covariance matrix of residuals that we obtained in the second stage. This allows us to incorporate the correlation between error terms of different equations. The -1 next to the sigma cap means that we have to take the inverse of this matrix. The I within this weight matrix is an n by n identity matrix which has 1s in the diagonal and 0s in all other elements. The symbol or operator shown here represents the Kronecker product of the matrices. This means that we have to estimate the Kronecker product of the sigma cap inverse and the identity matrix. This will give us our weight matrix for GLS. The Kronecker product in this weight matrix is calculated as shown here. The first element in the matrix sigma cap inverse is multiplied by the entire identity matrix. Since this identity matrix has n by n dimensions, it will yield a matrix of n by n dimensions. Similarly, the second element, that is, the element in the second column of first row of the sigma cap inverse is also multiplied by the entire identity matrix to yield another n by n matrix as shown here. This way, every element in the sigma cap inverse is multiplied by the identity matrix. Further, the resulting matrices are stacked in the manner shown here. Together, this will yield a weight matrix that has n by 2 rows and n by 2 columns in our example, where n is the number of observations. In general, the weight matrix will end up having n by e rows and n by e columns, where e is the number of equations in the model. You will notice that this matrix is multiplied with the z-cap transpose, z-cap and y in the formula. This means that we are assigning weights to the variables in all the equations of our model. In this formula, y is a vector of all the dependent variables of the equations. In our example, it will contain the consumption and investment variables. These variables will also be stacked in the manner shown here. First, we will have all the observations of consumption followed by all the observations of investment variable. Hence, this vector will have n by 2 rows in our example. In general, it will have n by e rows based on e number of equations to be estimated. Now that we have defined all the elements in this formula, all we need to do is use matrix multiplications and inverse to estimate the coefficients of the 3SLS model. The computations of 3SLS can get quite complicated. Statistical software programs such as R and Stata have packages and functions to estimate the 3SLS model. In the next tutorial, we will discuss how to estimate 3SLS in R and Stata. Moreover, we will also discuss some things that we must watch out for when applying the 3SLS model. Thank you for watching, and I will see you in the next tutorial.